Hello and welcome back to Evening Rust, a show where we do coding in Rust and either succeed or blame the language for our failures. That's how it seems lately, and we're going to keep up that tradition, and we're going to see how we do. Before we start, I'm going to show you where I am with Leaf, because Leaf is getting to have some fun stuff. I actually fixed a few issues today, some wonderful ones, so I have this wonderful example now, where you can see the whole wavy thing here. And this was actually crashing before, and it was crashing because I had an alloc-A in the wrong place. Alloc-A does a stack allocation, if you're not aware of this. In a stack allocation, it has no free counterpart, and in a loop, it meant every time the loop executed, more and more of the stack disappeared until it crashed, and you couldn't figure out why it crashed because the stack doesn't show up as used memory quickly enough, and the stack trace doesn't show anything and be there. But, anyways, I fixed it. It's great fun now. So this is perfectly stable now using SDL. And we're going to keep working on this. I think I'm far enough. I'm going to start doing streams on Leaf then to show this progression. What I'm going to do in Leaf is probably work on algorithms. Some of the algorithms we have from this show, Evening Rust. For example, the next one I could probably work on is the Tron one to show how we do Voronoi diagrams and how we do the filling and stuff like that. And because if you watch this show, you don't necessarily have graphics for that. And if I could get the two combined, that'd be great, but working at two languages at once is hard. So to start the show off, we'll go over to Clash of Code. We're ranked 177 apparently, because we play it so often. Oh no, there's nobody else here. Oh, we just missed one, I guess. Just filled up. And anything else I have to report? Anything else? Yesterday I figured out the problem with the code, and actually let me load this stuff up. He checks someday my desktop doesn't have anything revealing on it. Secrets. Secrets. The problem we had just is I wanted to have a global random number generator, and the syntax I had was very close, and it's not, the thing that was missing was this asmut part. And I'm not entirely clear if that asmut return. It's really weird, the option thing. I'm still not clear on it, but we had a more complicated syntax, but this one works. And this actually speeds it up. The bot got a lot more iterations through, and that pushed it up a little bit higher than the charts. But it was pushed down to the charts since yesterday, so we're not really that much higher. We're back to about where we started. We can look for ways to improve, but again, we're in debug mode. Everybody's in debug mode, but it looks like every time I can increase the number of iterations I do, the naturally better I do. And there are a few techniques that we can do, to improve the initial things, because the initial game, that's where the worst thing is. Our first move is essentially random. As is our second move, as is our third move, as is our fourth move. They're totally random. And the reason they're random is because we don't do enough depth searching there. And so what I thought, we have two options today. And the one we can do is offline learning. And what that can be is that when we have the first move in the game, there must be an optimal position to play. One where you have the most gains of success. And I'm willing to bet it's somewhere in the middle of the middle. I don't know. But we can run offline. Although we can't run many iterations offline we can run millions of iterations in release mode and see what happens. If I knew how to do threading, we could run even more. But we can do millions, and then we can just hard code it. So hard code what the first move is. Wonderful, there's our first move. We've run this a couple million times, and let's actually load that up so we can see it. And where were we in compete? Tic-tac-toe. So there's not so many people playing yet, and we're at 29th here. And we're going to have to see how we get higher than that. So we're really there's not another league yet either. So we're really competing to get higher in here. There's 29 people ahead of us, and we just have to get higher than them. So every little step's going to actually be an impressive improvement because we're right close to the top. And I'm going there's probably an exponential curve in difficulty getting up there, and we can probably see that in the leaderboard too. If you look at the top score, 48.9, and look how fast it drops 48.9 down to where we are. Where are we? To 33. It's a 15-point spread, and so that means there's a huge amount of variance that the people up above are like doing a lot better. So we can, with minor tweaks, probably get up to 20 again, but even at 20 is 36. So this exponential curve starts pretty hard. And wait, that was 48 point. Yeah. So we have a lot to catch up to. But anyways, as I was saying, if you can see, you can never see the board here. They always put the little title in the way. I just want to see the board. Let's play it. All right, we almost got to start the game here, so I have to stop explaining and go playing. Okay, but anyways, the first move of the game, I don't know who started this one. I got to start, and I only did like, for each big square of the board, I only did like 100 iterations of that square, and that's really not that much to know which one's advantageous or not. And what I'm going to do is probably run 1,000,000 iterations on an empty board, and then just hard code it where you play the first move. There's got to be a preferred place. And the second thing we could do is for the other people, it's for the other players on our second move. On our second move, they could play in one of 81 spots. We can also hard code that. We can play the games from all those 81 different spots and hard code the second move as well, in a table. And that might give us enough to get up a few ranks, because the first move can be, I actually don't know the game yet enough. Is it actually that vital, the first move? It might not now. Oh, reverse engineering. Well, there's not much to reverse engineer. Well, that's really not that much to reverse engineer. Print line. Something like iter-repeat. .take a.len. And then it's just a syntax here I'm screwed up on. I don't know for sure how to do the syntax here, and that's my slowest thing here, is I don't do this one. We're going to fight with this next. Basically, we have the logic now. Use of undeclared. What the hell is it? Is it just repeat? Well, come on. What's repeat? Rust repeat. So that's what's slowing us down. I forgot where repeat is. We even used this recently. How do we do repeat? Let's give you some example. Oh, come on. Aha! There it is. String dot repeat. Let's go back there. Or maybe we could just do it this way. Repeat a.len. There was supposed to be an iter repeat, but I forgot how that works. Oh yeah, it's supposed to be +4. They count for the end bits. There we go. So we had to look it up, so we're a bit slower than him because we had to look it up. With C++, oh yeah, he just took the quick way. He wasn't going to go look for the algorithm stuff in C++, what you had to actually do repeat. There is a repeater in C++ as well. But I'm trying to avoid doing that. I'm trying to avoid using fixed loops. I mean, I'm trying to just use the language. And I thought there's an iter repeat as well, but string repeat works just as well. I mean, I can't remember where I used the other repeat now. There was a way to do repeat on random things, and we used it. We used repeat and take, and we'll let them go here, the other 4 guys. I can't imagine they haven't figured it out yet. So far, the reverse engineering, there was one really tough one. I just didn't know what they were doing. But the last ones we've been getting have been relatively easy. And it's just been a speed contest. It might as well have been a speed contest here. Alright, let's go back to our game of tic-tac-toe. and I can show you what we did. So this global RNG, this is a lot faster than the built-in one, and in play I put a little benchmarks at the top. And I'm actually going to change this as well. So in strategy, next random, this is random. Get random move. Where am I? Actually, state's supposed to be here. Get random move, random. You can see this gen range here. I'm calling get global gen range, but this gen range is actually pretty slow, surprisingly. And so I put this output here, and if we actually do it here, if we do cargo build and clear and cargo build and target slash debug slash play. So right at the top I did the output of those timers, and using the random number generator generated range takes 222 nanoseconds, which is 2000, which is really slow. Really slow. Even for debug mode, that's kind of slow. But these are actually, I think, cryptographically safe, so they're default. And I mean, if you're going to choose in a language, what should the default random be? Err on the side of cryptographically correct, because you're going to have a bunch of people that don't actually look at it, just doing randomness, thinking, hey, this might work for this. So you take the most extreme example, even it's slow, and those of us that need something fast, we'll find something fast. So in global, so this is like this percent here, and because the gen range itself is really slow. Not as only is this generator slow, the gen range itself is pretty slow compared to this percentage here. So we can check that here. So I had 472, but if I did it the other way, if I did this random generator, and this is the fast one already, but still I do gen range on it, 0, board num cells as use size. This is still source. Remember, we have a number of about 500 right now. 472, 500. And look, it almost doubles in time to use this range function. And so we're going to, and the reason I did is because we're not actually using that one in the game. You're still using the range function in the game. So we're going to go over to the state, and we're going to use the mod operator instead here. So we're just going to do next U32 mod that. And we probably have to do a cast on here somewhere. As U32, of course. And generally when you're doing random, if you need correctness, and I got something on my glasses again, something landed on them. Can't see the screen. Mod is not it's not a safe way to do random, because it doesn't give you equal distribution. Now with a number as low as board num cells, which is 9, you won't notice it. It's when this number gets really high is where mod starts producing invalid distributions. And you can think of the reason for this is because if you say random is a number between, say, 0 and 1,000, but it's actually like a couple million or something. But pick 1,000, and then you do mod. And if you do mod 250, it's great. Well, you have 4 equal chunks at 250. But what if you do mod 300? Well, you get 3 chunks at 300, and then 1 chunk of 100 at the end. So there's like 66% of the numbers don't happen as often. So 33% of the numbers happen at a frequency of 4, and the rest happen with a frequency of 3, and that's a pretty big skew. But again, because the next U32 is really big, it depends how big this one is, how tragic that is. And for our cases, it doesn't matter. It doesn't matter anyways in our case, even if it's a skewed. But it would make a difference for skewing on us too, but the number's so small we're not going to see it. And you can't say next U size, so we're going to do an as U size here. And this should give us that. That gives us more iterations, and that's why I put the count. So that gives us actually a few more iterations. which is pretty good. That's pretty nice. That's helpful enough to get those more iterations. Upload. So with those few more iterations, you can test it, but then we can probably output it again. Although it was actually pretty high here already. So we used to do 90, 99, 108, and that's on my machine we're testing it. And we beat the default API, no reason to watch that. So look, we actually got, except for this one where something went weird. Wow. We got a lot more iterations. So we got like 10 to 20% more iterations by doing that optimization. And so we could submit that, and we might see a few bumps in the rank because we're close. But it's going to get harder to get higher. But we have to let it run for a while, first of all, to see what happens. See, now the next trick here we have is these numbers are still not very big. Right? Because in a Monte-Carlo tree, you're going to want to start filtering down. The numbers at the bottom here are fine. We do that. We do a split. But in a Monte-Carlo tree, we want to actually search the more likely scenario here, but at these numbers, our confidence is still essentially like random. Because if I have a free cell and I do like 99 iterations on it out of 9 cells, that meant I've evaluated 11 games on that one cell. And there's absolutely no value in that point to actually do proper Monte-Carlo because it's still essentially random. You want to have at least that number before you even start the frequency selection, the heuristic selection, not the heuristic, the actual selection phase. And by that, what I mean is that, let's play this game a bit forward. Let's go right here or something. I'm on this board here, and in Monte-Carlo I say, well, I have these 6 spots, and I'm going to sample 1 in each 6 of these spots. So I sample that spot, and then I play a whole game through it. I play a whole game through each spot. What Monte-Carlo says is that after you've done this a few times, well, let's look at the win rate of these spots. And the win rate, obviously, probably here, but you have to go over. If the win rate is higher for here, evaluate these ones more often. Because you want to increase the confidence here. Like, you want to make sure you didn't get lucky. And as you increase this more often, your actual win rate may go up or it may go down as you build confidence. And there's no point in evaluating one further that has a lower confidence because it's like, that's a bad spot. Why are we bother evaluating that? And so that's what the Monte-Carlo actually says. It says, well, let's evaluate them in order instead because, hey, it's better. And it can do that in a branching system. So after this one, we go into the next branch and say, well, there's 9 more here, and that's for the opponent. And for the opponent, we're going to do it the other way. For the opponent, we're going to evaluate only the ones that give the opponent the best score. And this is part of a minimax strategy then, combined with Monte-Carlo, because we take our best score, and then we take the opponent's best score, and we evaluate down those trees. And that's their best option, and that gives you more. But the thing is, if you understand, I'm doing not enough iterations here. So in the first games, let's ignore the first ones. So let's go down to here where we have 900. This is actually... 900 isn't bad. So 900 means if I'm on a full board, say here, and I had 900, that's 100 evaluations for each one. Actually, and this is actually high enough that sorting by winning preference makes sense. And because then when you get to the second level, if there's 100 each, down to the second level, there's still 10 for each. The opponent, 10's not much to do his level, but at least our first level we can decide, let's start filtering on the winning ones and improve confidence. And we may improve bias as well. But the unfortunate thing is that to do this sorting on win rates necessarily slows down how many games we can play out because we have to do a sort then. So it's going to slow down our code, which is not very nice. So there's that balance there. It has to gain you quite a bit. And we were high before. We'll see what happens here. So what other options do we have? Now, and I'm deciding what option we want to do first. The other option we have is because in the first part of the game, when we have it open like this, ignoring the optimization for first move, I don't think that's a big difference. We play something random, that's fine. We have the option of not evaluating the game so far down. Like, don't play it to the end. do a score at each pace. Do a score and says, well, let's score the board how good it is for us. Now, we don't really know how to score the board. We may be invalid, but that could certainly speed it up and get this depth a lot higher. So basically we say, instead of going all the way down, because there could be a maximum of 81 moves, and this game took 40 moves. Let's play another one, see how many moves you're actually taking. That one took 52. And we're probably always going to win against the AI because we don't know what he's doing. And 40 again. $32. Oh wow, depth pruning. We're going to have to cut it down a lot if we want to see an improvement. Because if we're getting down to 40 already, and that's about half the depth. If we cut it in half again, we're only going to double our numbers. There's really not, it's not like an exponential game because the tree branching, we only take one path each time. So, but if we cut the depth in half, we double our numbers basically. But then we have to come up with scoring, and scoring has to be fast enough. And scoring involves, do we have to score a board? It's one option we could try first. I'm not sure which one we do. Do we try the tree approach first, or do we try the scoring? Okay, so where are we now? Now in this league it's going to be very challenging as well because there's not so much competition. If we're already in the top 30, it's like we have to, and because of that spread, we have to make a significant improvement to get higher in the charts. And this is always the case at the top of the leaderboard, whether it's in like, well, it's different because there's no board above us this time. It makes it harder because if pretending we were in Legendary, we'd have the same problem in Legendary where there's no board higher than us. But we want to see if we can get higher right now. And so we're still going up, so that little tweak that got us deeper, that's a good sign that getting deeper is helpful. Alright, so what would we do if we wanted to... Let me close that, I don't know why it's open. In strategy, if we actually wanted to do the sorting, well, the best move at this board state we can't do much about. This is the one that says in the big board, either pick one cell or a bunch of cells. And those are just going to be fixed. Although even there, I know because we iterate down to the next move, it may not be very helpful. Yeah, we could see. We could improve that there. I don't know how often that comes up in the game where you have an open move. Okay, and the guest move in the second one, it would be somewhere here. And we have these board cells. We'd have to change these loops here. And we'd have to sort, but sorting makes it really hard because the moment we sort, well, we could put a triple in here instead of a double tuple here, I mean. And instead of relying on the index, we could go down and say, well, actually let's look up what value it is here. And that'll actually make more sense for I in 0 dot board num cells. This will let us actually sort the things. Cells tree I equals I, 0, 0. And this is actually cell Big cell? Little cell? Score. Oh no, num played. And in this loop down here, we have the I closed and put CS up here. Now it's CS.0 instead. So we could actually order these later. And this down here is CS2 and this is CS1. And why the hell didn't I give these things names? Are name tuples slower? Well, let's do that afterwards. Let's do this first and then check if name tuples are slower. Iterations here, we can see get more of them. And cell, comma, score. So we don't need to enumerate now either. Tree.iter. Oh, this is one of the problems you can use. What am I actually doing here? Tree.iter.enumerate. We don't need that. We don't need the map to T0. Something's wrong here. We shouldn't have been mapping to T0, should we? Because T0 is the little cell. Yeah, because we're stripping off the games played. Yeah, we're stripping off the games played, so that's fine. Let's just do this. Let's do filter, and this is going to give us big cell. So we filter out the ones where we can't play, which it doesn't actually do them in the loop, and we could actually filter that out now in here, but I don't want a dynamic number. I'd rather have a fixed number. And we can check if it's fast, and then max by key t dot, well, it's still surprisingly 1. It's going to be 2 actually. 2, because the 2 is the score. No. Alright, I gotta figure out what this is again. So we take the number of games played, this is the number of games played, and this is the score. And tree I. So this is the cell, and this is the score. And that's the num played, so cell, num, score, played. And so when we iterate this, we filter by cell, score, num played. Now if only if that, we don't need the score, we don't need the num played. And then we max by score and unwrap it, and then we get cell, score, and num played, which we don't need. And then that gives us that there. Clear? All good? This is using a reference. Do we have to have double referencing now? Come on. Filter. We don't need that. Okay, so filtering is getting annoying now. When I put there, it got complained as well. I hate working with these tuples and stuff. They're not value types. I don't know what the hell they are. I mean, this is one of my complaints about the language, is these things iter and stuff. I'm not sure what they're returning. They return weirdness, and then you have to deal with weirdness everywhere. Consider using a reference. This would make no sense whatsoever to put a double and here. Like something really wacky here. I have no idea why that is. Okay, so we don't lose any speed here, but now I'm totally confused as to why I have a double reference here. And this is what I mean about I don't like iter in the language. Because iter, whatever you have, I don't know what it iterates. It iterates like a reference and takes references that are references, and it's like, just do something normal. And it gets hard because I have no idea why I have a reference to a reference here. But I understand why if there's a reference to a reference here, why I have to spit out a reference here. But I don't understand why did enumerate then not have a reference, and do I even need the iter? Can I just filter? No, we can't do that either. You have to actually iterate them. Okay, now we could put the close calculation right in here, but it's not likely to be any faster, right? Because this loop or this loop here, it's hard to say what might be faster. So we have this, and it's a bit, we know how many we do, and it's unlikely that loop there is causing any issue of speed whatsoever, regardless of how we do it, because the speed problem is not coming from here. It's coming from this function right here, play to end. Play to end just dominates. This thing here is just ridiculous. How far are we in the game? 24. We actually made it slightly higher, so the slight calculations. I mean, this could be randomness here as well. Still going up slightly, so we could get power. So we got it up like 1 more point. We got past patata. Got past the potato guy. Stuck between patata and gata. These guys are in the competition giving us problems. A lot of names we recognize from the competition. Aw, the potato got past us. Alright, so then we have to check the next one here. And this is going to be a pain in the ass. How do we want to check this? And how do we want to run multiple passes? And so let's just do a sort first. I wonder if we can sort a vector. I mean, whatever those things are called, an array. It's not a vector, it's a sort of a basic array. I should be able to. It's a slice, sort by key. So let's try it. And that's going to happen down here. Each time we do the loop, we want to sort it. So tree.sort by key, and this will be t.1, the score. Just make sure if this works first. Okay, and so we haven't changed the game any, right? We've just sorted it, so we have a different ordering here. Now what's going to happen here is we're going to have a double loop here. And the double loop, see the first time is, like, I'm trying to show you, the double loop is the first time we go through, we want to do a certain number of iterations for each of them first, but once we've done a couple of iterations, then we want to switch to a different mode. We want to switch to a mode where it's like the top ones get more iterations than the low ones. And so the ones with a higher score get more iterations. And try and think of how's an easy way to do that so the first time is normal and the second time is not. Well, we can risk it and the first time actually do more as well. And we can just simply do a bias here. But we have to know how many we have free though, don't we? Okay. Knowing how many we have free is going to be helpful because there's only 1 or 2 free. It doesn't make a difference. Well, let's just do that. Let's just do that fixed bias here. Let repeat equal I is greater than, or I is less than, if I is less than, let's say, 3, then we do a repeat of 2, else we do a repeat of 1, and we just do this 0 dot dot repeat. And I'm hoping these actual loops don't cost us more. And what we've done is basically said the ones that are in the first positions, the higher scores now, we'll iterate them 2. The first time we just iterate the 2 at random, but if it's... And that, it won't change the number of iterations, but it changes the score as we explore the winning path a bit better to check, to improve our confidence on it. And this is going to be really, really hard to check if this improves our game or not. I mean, obviously 0 wins here, and the number of variations has varied a bit more. It's hard to say whether that's good or bad. Yeah, that loop's dropping us down. Well, it could be the sorting, but the sorting slowing us down. Like, what if we took out the sorting? Do I get the iterations back up? No, so the sorting's not the issue. It might just be randomness on this system. So we built this, and then we can see where we are in the game. Now, this bias alone may or may not give us confidence in it. What it does is it helps if you have a couple that you're deciding between. It evaluates those more to between the couple that are good to say, well, okay, which one's better of the ones that are good. And so we're at 33, so we're still technically going up. But let's submit this here, make sure we win, and then we'll submit it again. So we're at rank 25. Let's write that down so I remember. And we'll submit. And see if that preference gets us anything whatsoever. We lost a whole bunch there at the start. The problem with the preference is that the ones that get a bad score, we could prematurely be filtering them out and saying, hey, look, you know, that was terrible. And we still haven't evaluated the tie correctly yet, so we should actually go and do that. So in the case where the big board is a tie, we're actually supposed to count the small boards, and I should definitely go do that, because that'll make a difference, because that ends the evaluations differently. And that's probably actually more important. But let's pretend we didn't modify that first of all. We're not going up so fast. So this was my fear about the small numbers, that if we already start filtering, we don't have high enough numbers to make it worthwhile. And it looks like it's actually made us worse by preferring those ones. So we're not getting a fair evaluation of the things. It just hurt us. It's really just hurt us, it looks like. So that's not going to help. And that's why I said that was a bad sign to begin with. When we don't have enough evaluations, doing the actual confidence stuff on the Monte-Carlo isn't going to help. We'll let it run for a while, but let's see where that ends up. And so that was my fear. With such a low iteration count, is that this filtering stuff doesn't help. And the fact that the sorting takes time hurts us even more. Let's put this like this first of all. Put it back to the way it was. Well, we'll see what happens with it, because we got more. Actually, we did, and so that actually we get more iterations without it. Not a lot, a tiny, tiny, tiny little bit. But it could be enough to make a difference. This evaluation here also takes time, but again, probably not. Although, it could take long enough. That seemed to hurt quite a bit. Were we doing it right? 0.rpt, yeah. CS.2, 1 games played, and the match value. Yeah, we're doing that okay. That makes a huge difference. That's really weird. I'm not expecting to make that much of a difference. It's just we don't have enough iterations. Unless just the looping setup costs us even more. Right, in the optimal mode, you want to strew out some of this stuff, but again, I'm not worried about the outer driving loop, because again, it's this play to end, which is probably killing us the most. Let's actually look at play to end and see if there's a way to improve. There's no way to improve this. Each move, we check the state. Get state's going to be a slow function, I think. Let's find out how slow get state is in this form. Call get state quite often. Get state, as we recall, is just this big loop. We go through this loop, and in release mode, you'd expect this to be unrolled. There's 8 win conditions on the board, and 1 final full condition. Let's see how much this actually costs us. We get rid of some of the random numbers. Copy this again. Should do this function perf. So we can separate that out. Repeat 10, separates out. And what did I actually want to check? I did this global here thing twice. Global, I want to do get time. I want to do perf and s. State is a board state. Now s dot get state, get status, get state. Get state. We'll see how long this takes. I'm hoping that, like again, in release mode, that should be pretty close to 0. ST. Expected a literal. Alright, that can only be a literal. Well, why do I even do that? Just do this then. Did you mean G? No, I didn't mean G. Oh, I went state, yeah. State. Oops. State s dot big. Oh, come on. I called the wrong one. State.board. RLS was working earlier, and it stopped working again. It's very picky. 58 state.board.big. Get state open. I forgot to report the time. Be helpful to report that if you're trying to do a performance test. Get best move cost 96 volt. Yeah, we don't even need to time that anymore because we have it fixed to time, so. And we probably should write. No way. 2 microseconds. Ouch. Wow. To compare in release mode, let's see with that. So 2 microseconds for that get state. In release mode, like, it's really just a bunch of bit operations. And still, 263. Okay, so there's something going wrong there. This function should not take that long. We're going to resort to a macro then, because even in release mode, this is not compiling well. Now, somebody said Rust was inefficient, but like, this is really bad. I fear it has to do with these lookups here. Is there any way, they're probably doing like a bounds check each time in the loop. That could slow it down a little bit. And so let's take them out. Let's see if that actually makes a difference. Ah, come on. Let P0 equal self.board 0. Let P1 self.board 1. This will confirm whether that's actually a problem or not, that lookup. And since it's a safe language, I imagine it is, because it's not going to let you look up something that's not there, so it has to do bounds checks each time. This win state's 8 though, but still, yeah. 8 times 8 bounds, that's, so this is 9, it's 8 items, so 8 bounds checks times 2, 16 bounds checks. Shouldn't account for that time though. Two on 12, did it actually change anything? No, not really. The variation's too low. Really need the benchmarking on that. The variation's a bit too low there to actually do that, so let's just do this in a loop for I in. It's not gonna do it. We should do this in the benchmarking tool. I forgot how to set that up, but I'll just do it in so whatever the hell we submitted last time is terrible. So that pretty much kills the plans for the Monte-Carlo approach. So that's what's killing us a lot. Because we call getState every single time we take a turn. So let's go to macros. How do I do a Rust macro again? Macro, I forget the syntax. Well, that wasn't helpful. Show me a macro. Let's just read the older page because I don't think that's changed. So we have macro rules here in state. What I'm going to do is I'm just going to inline. I'm going to unroll this thing on my own and get rid of the loop. Macro rules. eval player. What do these take? These take a they never start with these. They have a lot of documentation, but they never start with easy ones. So they had a tech writer that did like a whole bunch of work, but they're not always clear. So here's a clearer one down here. This should have been the first one. $win, and this is an expression, I guess. No, it's an expression. It's a literal. I have no idea what it is. We want to say, this is where we have this, if P0 and $win equals $win, return game result win 0. Otherwise player 2 win. Just get rid of this big loop here. The bottom thing we could probably leave the same. We got to copy these values out though. So eval player, and just stick these in here. Ah! Still the editor. Oops, I forgot to put an exclamation mark. So we're going to manually unroll, get rid of all the vectors or whatever it's doing. This gets rid of every single, any bounce check or anything. And I would hope that, you'd hope that release mode would have done that anyways on the loop. But sometimes, but it might be too big to unroll it, and because of this AND thing and stuff, it may just screw it up. This bottom one here, there's no point changing because that's as small as we're going to get. Let's see how long it takes us now. Hopefully it's faster. And why can't it use P0 there? Their stupid book. Again, this is bad UI design on their page here. Because when you click over to window here, you end up loading the next page. And it's the whole side of the window. So it's not just the button, it's the whole thing. Why can't I use an external value in there? Do names not get introduced into it? And let's just do it this way. There's an ident in here somewhere. So you can actually introduce variables. Somebody said you couldn't do that, but it actually just says it can work. But it doesn't look like it pulls variables in from the outside, which really sucks. I don't really want to do this. Those are probably expressions. Okay, we get a substantial number more evaluations here. Look at the speed prove up. We've gone down to 364 microseconds compared to 2,000, and you number the iterations here. We've basically gone up 2.5 times the number of iterations we get now. So the Rust compiler people doing optimizations, they should really look at these types of loops. I don't know where you'd report this type of thing, because this loop is not being evaluated well. Now if we do this in release mode, you can see how long this takes now. Now look at this release mode. Now in release mode, we're getting like, this is a substantial number of iterations at the point. In this first part of the game, we get 3,000 iterations, and this is times 9 times 3,000 per square. Then we could really do good stuff. And get state is still taking 261 though, which is still slow, and I'm still shocked by that. I mean, this is still amazingly slow in release mode, but it doesn't cost anything more in debug mode. Debug mode is slightly slower, and I have really no idea why it's taking that long. Is it because of these lookups here? Let's see how much these lookups are actually costing us. Let's just say 0, U16, U16, and then we can figure out a way to do an unsafe lookup. And it went slower. That makes no sense. What? Oh, I know why it goes slower. Because it evaluates the whole thing every time. Alright, but what we're going to see is unsafe. Unsafe fast vector lookup. Let's look up how vector works. Let's look at Zeal. And I wish it'd stop. This is useless to me. Don't do this. I can't install it this way. That's just in the URL. Rust. No, this is an array or something. This is an array, and is there anything unsafe here? There's no search functionality. What I'm trying to find a way is to get it to avoid doing its lookups. I have a feeling this game result's also a bit slow. Well, we got a lot more, so let's just submit that first, cargo build. And that actually gives us more evaluations. We were at 25 before we submitted this atrocity. But with more evaluations, that atrocity might actually work. Looks like at least 1,000 we need to get there, so submit that. Just give me 1 second, I'll be right back. Alright, sorry about that. So that's where we were before at 46, and I mean we were at 25. We want to see if we get any higher. We do more evaluations now, and in theory that should put us up higher, but again there's also other people submitting, but not that many. We'll just evaluate a tiny number of them. So this optimization here would really help, and I really want to find a way if we can do a quick lookup. So we don't want to leave that open because we know it still crashes. So with Rust, I want to do a Rust fast vector lookup. I want to do it unsafely. And this is actually a slice lookup. Fast, unsafe slice lookup. I don't know how to do this because that would probably be faster. Box slice, no code is. I don't know what that is. Pointer, offset, Rust offset. Is there something called offset? Calculates the offset from a pointer. Well, let's try it. Let B be a pointer to, well, we don't have that. These are actually pointers, okay. Const u16 equals self.board.as pointer. I don't know how this stuff works. We're going to find out. Do pointer dot offset 0. Pointer dot offset 1. Unsafe. It's probably going to complain about being unsafe. Oh, that would probably be called B. B. Call to unsafe function. I'm fine with that. So we can do unsafe. Unsafe. Oh, this has to be a block. And we should still keep the semicolon on there. Oh, come on. What's the type of this? Guess we have the wrong type. Well, it's U16, so let's just make it a pointer to U16. No, it's const. Why is it getting that type? I shouldn't have to do that. Oh, I know what it is. Oh, come on. It's this stuff. Because the unsafe block has to return something. And that slowed it down. Brilliant. It stays now 820. Come on, that can't seriously slow it down. And it makes it awful. But not in release mode. In release mode, it speeds it up, as to be expected. But in debug mode, it slows us down. That's really screwy. That's just screwy. And what the hell happened to our rank? I think it just failed to update it. There we go. We're 25. Still stuck at 25. So more evaluations isn't helpful, but it will help our strategy overall if we get this faster. So this is a big crux here, is to get state. There's not a lot of ways to make this faster, and I'm really shocked. There's something broken with that, but again, release mode's and debug mode's broken in all programming languages. It does random shit. And so in release mode, that was faster by a little bit. But this is faster in debug mode, which is unfortunate. And all these return game result wins. This is like optimized, horrible optimization. To the bottom is maybe they're costing us something too. And let's check this bottom one here. If we actually do this, if we just do this and do an else instead and get rid of the return, if this actually affects anything. I know, but that debug mode is taking a long time too. This is very variable here. And the iterations, it's hard to tell. The iterations didn't go up from that, but they didn't go down either. My fear is the cost of creating this game result and this type of enum. This type of enum, I think, is going to slow us down. So let's do this. Let's win. Oh shit, we can't do a win one there either, because we're going to have to pass it into every single one of them again. Let's make a new variation of this. Fun, fun, fun. And I think this lends to the maturity of the language. The language hasn't been around yet, but these are the types of optimizations that if you're doing C or C++ or something, this would be optimized away to nothing. But it must be something in the Rust language right now. They haven't got the pattern into the optimizer yet to get that working. So what I want to do is I want to say we're going to have another macro rule now. Eval bit. And this is simply going to be p0 and win equals win. It's going to return that value. So what I want to do now is I want to do if eval bit p0 comma this, or I'm going to duplicate this the whole way. Let's just put it this way. This will reduce the number of branches in debug mode. In release mode, you wouldn't expect to do a big difference, but this kills all the branching. It gets rid of the branching. And if there's any cost to this thing here, game result. But of course, it could do more evaluations now. That's the issue, right? We don't know how the laziness is. We don't know how it's going to evaluate, so we're really just checking stuff at random. Let's do that again for P1. We just want to see, this gives us insight into how the compiler's thinking as well. Oh crap, I forgot the exclamation mark on all of them. And, well, broke. Well, that just broke it. That's really odd. Oh yeah, because I got these in the wrong order. Well, rather than change that. That looks like it's slower. Significantly slower. We get fewer iterations, and the number's actually slower. And in release mode, is it faster? Yeah, we're not getting much. So, okay, that's not gaining us anything, so let's get rid of the ugliness. That didn't actually gain us a lot, so the branching hasn't changed. Yeah, this is actually getting us more iterations this way. I'm looking at the iteration. I'm not just looking at the number, I'm looking at the iteration count here. It's higher this way. So that gives us more, and this thing's not updating up there. Well, yay, we got to rank 24 instead. Okay. So obviously getting more iterations is not going to be enough. Let's go back to the debug mode. And how many iterations do we get now? 200. This is like 3 times as many as we had before. What I'm looking for is a high enough count that when we choose a move, if we actually built a tree and maintained a tree, we'd have some moves from before based on the move they did. But when you have, so that 200 is actually for one of the cells. If they're going to divide it by 9, that's going to be another 20 moves. We're only going to have 20 moves stored in the tree in advance, and it's really not enough to make it of any interest to keep the tree around. But nearing the end here, so the first moves suck, but nearing the end, where it's probably more critical. So if we iterated 7,000 moves, and those are our moves, and we say we had a full board, which is unlikely. We'd say there's like, say there's 5 free, or just say there's 1,000 per cell. That's 1,000 moves per cell, and then the enemy has 9 moves as well. That would get it down to roughly 100 in advance. It's still not that much. And what I'm thinking is, if you kept the tree, when you keep the tree around, you get to, you can kind of, when you keep the tree around, you can better evaluate the next turn. You have some leftover tree bits, which speeds it up, but 100 left doesn't make sense. But more importantly, you can predict better what the opponent would do. And that would be the next step, is we predict the opponent, because if we keep the tree down to 2 levels, then we'd have the opponent score, and we'd start making the opponent do the nice things, but unless we have thousands of them, it's not going to work. So I'm trying to think of what else we could do to make that work better. Well, I guess we can do the heuristics then. Scoreboard. Try that. Improve speed. Well, actually, we have to do a score the whole game as well. State.big. We're going to do the state.getState. State needs a state as well. And we can actually optimize this so that we don't have to call getState every time. We can do that afterwards, though. So the state actually needs something pub function get state for one variation. Because right now when we call get state on the big board, we'll just do this. So if you get, because when the big board, if the game is a tied, we don't consider the counting of the small board. And it's a bit slower, but, and match self dot board. Actually, we should put this as part of board. Board state. Self dot big get state. And if it is closed, what beeped? Something beeped at us. Euler finally decided to start following us. Well, thank Euler, Shasal. I thought you were, but okay. So we got that there. Good. Clear those out. Where are we now? Twitch chat messages aren't showing. Oh, that's bad. So I don't have chat messages. This is weird. Alright, so we're trying to figure out where my chat messages are. So apparently somebody's been writing to me? It's working? Was it not working before? I know it's been quiet, but I mean, sometimes it's just quiet. It wasn't working before. Well, shit, that sucks. I tried a new way of opening this window. Maybe it broke. Well, it's working now. Sorry about that if chat wasn't working. I hope I didn't miss anything important. It's a bit weird. I don't know why it wasn't working. Okay. It's got the same URL. I just reloaded it and typed something. So we'll have to check that next time. When I start the show, I'll type something more in there and see what happens to it. And unless I accidentally had two of them open. We're still taking a look. Okay, so where was I with that chat? Sorry. Tom, if you're referring to the play wrapper code, we actually used most of this code for the game evaluation itself. So it plays through a game, but the actual game state is all what we actually submit as part of the robot. Alright, so we're here in the big state, and we're just going to return this. Other, and you can just return other. Okay, so in the big state, we return other. Now when it's closed, we have to actually figure out who wins based on the count of who wins the small boards. So we're going to say let mid score, and this will be for score 0 equals 0. And then we say for I in 0 dot dot board num cells. We're going to do a match self dot small I dot get state. So this is really slow, the evaluation in this case, but that's okay. Game result win X. And we're actually going to return X equals 0. We're going to return 1. Otherwise, we're going to return -1. That's -1. I get the syntax wrong all the time. So now we have chat working. I expect lots of chat. Okay, so now we have match self small get state. So what I'm doing is that on the closed boards, I count the individual cells in the small boards, we add them up, and we could actually probably do a mapping of them, but I need to do this instead. And we're just going to say, thanks, Super Smurfin. Lots of chat. Love it. So we add that result there. Right here. Yeah, no, I plus equal. SC0 plus equals. Could probably do a sum on this, and everything else just becomes 0. So closed and open boards don't count, but there shouldn't be an open board at that point, but it could be. Because if the big board is closed, it means the small boards must be closed, but it doesn't matter. We still need the case anyways. And so this returns SC0. And what the big game get state does is it takes care of the case which we're missing before, is we weren't considering the whole, if the big game was closed. So if like nobody won the big game, we weren't counting the individual game scores, and that would make a difference in the evaluation then. I don't know how much, but apparently we get there quite often. And game win, this is supposed to be this. Game result, and oh yeah, so if SC is greater than 0, this is going to be game result win 0, because that's the score for player 0. Else if SC0 is less than 0, then we say game result win 1, because that was against him. Else it's game result closed. I think that's a tie in this case. Super tie. Now that cuts down our iterations ever so slightly. But it should evaluate more boards for us better. Why is this not updated? Silly things. So we're ever so slowly going up. So if we just left this, we get higher, but that's no point. There's no value in that. We're going to submit again and submit again anyways. So we're going to see if this improves it. So what we did, Tomcast, yes, what we have a bundler file, and that's in our TOML. When we build, we run bundle, and bundle takes all of our individual files, packs them into one thing called single file, and you'll see it here. You'll see the single file here. And that's something ePens wrote, the username ePens. And then over we have the CG local from Jasper, which takes this single file and sticks it into the game system. So we can write proper Rust code and then have it uploaded for us. We don't have to work in the single file here. We can split it out, use modules and everything you'd expect from Rust. And yes, it's definitely very cool. And it would be insane to do without that, to have one big file you're uploading. That would just be no fun. And so we have it proper. That also lets us do, like, we have tests. Yes, I keep track of these. Steve, here we go. If you just scroll down, these are the tools I use. The tools we use regular. Jasper's external editor. ePens is Rust source builder. Those are the two tools I'm just using combined together that get that done. And excellent little things to make coding game a lot nicer for Rust. I'll keep adding other stuff on here as people add things. I have a cheat sheet here somewhere as well. I don't know what happened with it, but okay. We'll keep adding that. Alright, so yeah, well, if anything we say we'll add here. If we do anything in the game, somebody says you should add it to there, just let me know, and I'll keep adding stuff to there. So we played the game and we won. And we're going to submit this again. Where were we, just to find out for sure? We're at track, let's say we're at track 24 with a tendency to go up. And the score is higher, which is good. Hey, thanks for the subscribe, Tom. Really appreciate it. Now let's do the upload to submit. And we'll see. again, the only variation I made now was to evaluate the tie boards better. And so when we get to a tie, I would evaluate who wins, because before I was just resulting as a tie, and that could actually make a difference. Depends how often ties come up. Just ignore the ones where I lose. And well, we jumped up pretty high to 24. Oh, we dropped back down. He just jumps all over the place, so it's kind of random. And unlike the game, unlike, say, the Borders of the Galaxy when we're doing this, there's really not a lot of value for us looking at somebody we're losing against, because we know why we're losing. Like, the value of the Monte-Carlo here, optimizing this, we don't care. We're not competing heuristics for heuristics. We have no heuristics involved, so there's really no value in looking at the reasons we're losing, because we're just not losing because we're not looking for enough ahead. But if we had one like these guys here, so if we had Fenrir, if we realize we lose all the time against this guy and he's higher and he's lower in the ranks, for example, that would be interesting. That would mean there's a heuristic where we lose. So let's go look at where Fenrir is. And where is Fenrir? So he's higher than us. And so it's possible he beats us more than once. But if we end up with a rank higher than him, that's an actual case where we can look at. That might imply that he's doing some sort of heuristics. And he's finding a way to beat us despite our Monte-Carlo. And so we have to check that in the end, who we lose against and who we win against. Because that actually points out that there are heuristics we could be doing. And we know the big one we could be doing of scoring the board. And so we're beating him, right? And this is the big case, is that we're beating a guy that beat us twice, which is kind of like a warning flag. That he has an approach that's obviously, it's not Monte-Carlo based, because otherwise he wouldn't beat us. I mean, he may have got lucky and beat us twice, right? We're using random numbers. It's going to happen. But he's actively submitting now too, so we don't know what his rank is. If his rank ends up higher than ours, then we wouldn't be concerned. But it looks like we're going to end up with a higher rank than him. So I wrote Fenrir down because that's one of the ones we have to worry about. And who else do we have against? Who is this? Bob. I think I saw him higher in the charts though. Fenrir and Bob are the only ones that... And who's this guy? Neumann. Neumann, Bob, and Fenrir. And where are they sitting on the boards? Where is Bob sitting? At 41, right beside us as well. And Neumann... Okay, Neumann is really high in the list, so he's just got a better Bob. We don't have to worry about him. It's Bob and Fenrir, which are kind of like, what are they doing that are beating us? Did we just get an unlucky run twice? It's possible. So let's go grab Bob and see if it was just a lucky run from him. Bob, hey Bob. And we'll play a few games against him, see if he's getting lucky or he actually has some sort of heuristics involved. Because we know if he had a better Monte-Carlo, if he was able to search better, overall better search, he should be higher than us in the ranks. But he's not. Okay, so this one we won. Play again. Another 1-1. Play again. I think Bob just got a lucky run against us. Four. Yeah, it really looks like Bob just got a lucky run against us. Okay, one loss. Alright, let's do one more and we'll see. It's the nature of randomness. You lost. So it's not like he has some fundamental way he's beating us. Luck of the draw. You start using random number generators, that happens. And let's check for Fenrir what happens. But he's higher in the charts now. He's up to 34. We won that. We won again. Alright, so Fenrir's probably got an equal quality bot and got a lucky run against us. So that's 3 for 3. Right, and here's when we lost. So I think he got a lucky run, but he's doing a bit better than Bob. Now, because it's random, and this is why you no point in playing this, we can replay and we're going to get different results. Because random number generator is going to do something different. Because the games, there's no difference between the games other than who starts. And when we played that and it went down, unless it somehow keeps the time the same, which I doubt it. Yeah, so replaying against these guys is also totally pointless. If he's just doing like a look ahead, we see no strategy heuristics, so there's no point in playing against them at all, other than to verify that we're there. Where do we manage to get up to, though? So we are going higher this time, though. So that board tie evaluation does appear to help. And I mean, sure, it's 23, and we were at 24, 25 before. But again, remember there's a ramp here. There's an exponential ramp in these scores that every little spot could mean an improvement. Or not. So, the next approach, we'll see where this goes up to. It looks like the general trend is upward, so maybe we get a few more points. Get status, get commits. And this is eval tied boards to the small board. The next thing we have to do, because I think we've optimized out... Oh no, we have one more optimization we can do. And this was in strategy, this play to end here. Now, I'm trying to think of how we do this play to end. The logic is that this take turn it would know whether the game state has changed. And because this game state function is expensive, we want to know whether we can check to see whether this game has actually changed state. And we can cut out some of these, and that would give us a higher iteration count. Who knows how much? Right now, because when we go to play right now, local play, these numbers here, the first, or maybe the first one, so 234, 279, these are about the numbers you want, 234 to 279. Those are the number of iterations that we get, and there's 8 of them, or 9 of them for each of the board cells in the first move, and these next moves are the ones, one move in to 500 or something. And we have to see if those numbers actually go up. Okay, and so this take turn here, when the small player, when they take their turn, and then we check the state of the small board, if the board is still open, it means it's impossible for the main game state to have changed. If the board is won or the game is closed, then the overall game state can change. And the vast majority of moves, and especially in the start of the game when it's most vital to get more iterations, the vast majority of the moves are going to result in open. So take turn now is going to return 2 things, not just a board index, it's going to return a bool as well. And the bool is going to be force comma state change, where force is the position and state change. I don't know why I'm putting docs on it. State change is, could the game have changed win states? And so now we say let mut change state equals false. And these two here we can say change state equals 2. It's true. Change state equals true. And then at the very end we're going to return that in this horrible approach. Change state. Now whoever calls this change state, or we call take turn, is going to have to deal with that now. Find in files, take turn. And we can just ignore it here because that's not our concern there in our play code. We don't care here. We only care in the strategy code. Our play code doesn't matter how long it takes. And oh no, man, this is gonna we can't. I did it wrong. This is gonna have to be .0. The main game code doesn't care either. This take turn ignores the results. I don't know why Rust lets us get away with ignoring values, but okay. Take turn. And this is where it kind of sucks in Rust. You can't just do like comma something equals. You have to like have a temporary now. As far as I can tell. QF, QS. I don't know if anybody could tell me how this one works here, QF, QS, and then we'll deal with the QS afterwards. And get best move score. Take turn, play to end, doesn't matter here. And here we can put that, because here we have a let, so we can ignore the second value. Test turns like Q, comma whatever, you can ignore that as well. And we're probably going to get some errors. Yeah, right there. That's on play. Like Q. No, we can just do it this way. Just do, since we're just ignoring it, .0. .0. Just make sure it's still playing. And again, if you're watching, our play game is supposed to always have player 0 winning. So our play setup, what it does is the game, it sets up a board, and then does random, well, it used to do a random 20 steps, now it does a random 0 steps. So let's make it do a random 20 steps again, and then it plays to win for player 0, and so it's supposed to be always player 0 winning, regardless of what it is. The random 20 steps could sometimes let player 1 win, just because, you know, in a random 20 moves it can win, but right now we have that 0 winning. But now we've changed our iteration counts because we don't see the first move, so I'm going to change back to player 0 winning right from the start so I can see those counts. Now it appears to have reduced the number of iterations we can do. Yeah, the numbers may not be significant. But what we want to do in the strategy now, in the costly place here, let me change state. And we're going to say true because it has to evaluate at the first turn. Because the play to end, where we call play to end, it doesn't evaluate whether the board's already done or not. So it has to evaluate at the first turn. So if change state, then we evaluate the game board. Change state equals QS. Now again, I'd love to see the structure improved here. I don't know how that's done though. I'd like to just assign directly to both of those, but I don't know if it can be done. Now let's see if we get more iterations out of this. And It honestly doesn't look like it. It's really hard to tell those numbers, but it doesn't look like we get any more iterations out of this. And we don't even get any up to, well, it's strange we don't get any more. I was expecting for like a 10-20% gain or something like that, because that get state function is very, very costly. Where are we now, though? We're stuck at 24. Alright. So getting more iterations is not likely to help, but we can submit that again anyways. Again, if we waited longer, we'd get probably slightly higher. But it looks like we're going to have to go do something different. We're going to actually have to do some sort of heuristic on this. Because I think we're maxed out the iterations. I mean, in debug mode, and again, in release mode would be faster, but honestly, if they turn release mode on for everybody, we'd be in the same spot. Except we saw the C++ guys then would be even faster because Rust is still slower in release mode. So some of these functions we're doing in Rust, they're still taking too long in release mode in my system. I mean, like that get state function should be like 30, 40 nanoseconds. I mean, that's how fast the system is. It's like a 4 gigahertz chip. It can do 40 operations, and that's all that function does. It does like 18 compares. That's it. And those are all single cycle instructions. So I have no idea why it's taking so long even in release mode. It's taking like 200 nanoseconds, and it should be slower than that. I mean, it should be lower than that, not slower. And Recurse here in Canada, he's doing amazingly well. Whatever his bot's doing. And we know that they can partially cheat in C++. You can enable release mode. And that would definitely help. But we presume these other guys know it as well. So Recurse here definitely has something stronger. And he's one of the stronger people on this system. And he's like really high up there. He does well everywhere. 9th overall. Haha. I just follow him because we always see him. And he's in Canada, so that's where I'm from. I'm in Germany right now, but I'm from Canada. So he's number 9. So I'm going to say, if we ever get to the point where we're competing with Recurse, we'll be happy. And that's with any of the games. He was in the competition tier, and he was doing amazingly well there too. And I don't remember what the final results were. I have all these French guys. Okay. Ah, Winter Squirrel. So you're also from Montreal then, or from Canada? Yeah, that's cool. Good to see a small community. Boris, our Go guy's always there. Who else is doing Rust right now? And this will be the good check, is Rust. Okay, so we are at least faster than the other Rust guy. So I can't, I mean, it's by being faster than the Rust guy, we can say, okay, good, you know, we don't have to worry that somebody's doing Rust faster. The worry here is that if you see somebody with Rust sitting up at number 5, you're going to go like, yeah, okay, my bitching about it being too slow apparently doesn't apply because somebody else is using Rust and getting up there. But you notice our score is getting a lot higher than before. And we should actually be tracking this score. Now, the reason we should be tracking this score as well is because as our score improves, it means we're actually getting better. But we may still be doing the rank lower in the ranks because as the variance increases as a top thing, as the top ranks, we could actually be getting a better overall rank against the lower guys, but because there's still better people out in the deviation, we could still be sitting down lower in the score. Because we were at 33 before, now we're up to 35. And look, there's this 1.5 point gap here to 25. There's already a jump here. Okay, so what do we have now? We can do some sort of heuristics now. Did I commit this? Git diff. Oh, our git diff's useless here. I have to do the tree diff. Now I have to close all these windows. There is actual tree diff, but it's not the default, unfortunately. I just wanted to see that something was changed. I should type status. Alright. Now I'm actually unsure to submit this because this made no improvement. No, I mean, it's a wonderful font. Everything's nice and clear, nice proportional fonts, beautiful. Not odd, beautiful. Reduce get state calls. Now this may have not made a big difference because every time we take a turn it has to do a get state anyways, but we may have cut out just a few of them. I don't know. And let's check it out in release mode whether we actually managed to get something faster. So those numbers are higher a bit in release mode. It's hard to tell. I'm just going by my intuitive, innate human ability to quickly scan numbers. And it looks like this actually helps in release mode a little bit. Well, we're not in release mode, we're in debug mode. But I think that's it for optimizing bare bones optimization. And we're still not high enough to do better tree evaluation Monte-Carlo style, right? Because 1,000 iterations is still not very much. So we're going to have to do heuristics now. And that's basically this play to end is going to have a cutoff point. The play to end is going to say after 20 moves, I just stop. And let's take a turn, and let's predict who wins. So we have to make a prediction here. Based on this board state, we'll make a function called predict state. Predict state and self. Game results. So how do we write a predict state? Hey Mystery, welcome to the show. We're currently trying to write a prediction method to determine, given the state of a board, like say here, I want to predict who would win this board. Mystery, yes, you can definitely do it as a beginner. There's a lot of practice things which are really easy to get into. The multiplayer bots, what we're doing, you can definitely code and you can get into it. If you're an absolutely beginner to AI, you may not get very high in the ranks, but you can definitely play it, and there are definitely places to learn, and you can learn a lot about algorithms here, and I definitely encourage doing it. You can definitely learn a lot about them, and you can learn some AI. Some of the games are easier than others. The practice games are great, and especially the ones with graphics, and some of the compete ones are also good. I mean, just getting a tic-tac-toe bot that works, even if you don't get high in the ranks, is still an impressive feat for a beginner to do with algorithms, so I encourage it. And again, there are other ones. This one's one of the easier ones. Some of the multiplayer ones are really tough to get into, but this one's relatively straightforward. So is the Tron one. The Tron one's also relatively straightforward. Okay, so now we need predict state. How do we predict the state? Well, we need to predict state on the small boards as well. And predict state is allowed to be an expensive function. Maybe. This is an issue. If it's too expensive, okay, we're going to put a predict state in the small boards first, because we need to know in the small boards, the individual boards, what is a small board, what is the predicted state of the win. Predict state. Now the first thing we do is get the state, because if the get the state is closed or whatever, then it's done. It's only if it's open. So we're going to return match self.getState. And if it's open, that's when we have to actually predict something. Result open. Now, you can return match directly this way, and I actually don't like it. I want to make this function closed. If it's something else, I'm going to do a return queue. So I'm not going to do a one return here. I'm actually going to do multiple statements just to keep the code from getting too long. Mystery, how long did the challenges last? These ones are open. This is an open leaderboard. There's no time limit to them. Most of the games are all open leaderboards. You just commit whenever you want and watch where you go. It's only the contest, and the contest just ended. Contests have a 10-day limit, but they only come every couple of months, and only those ones have a limit. Everything else is open. Just take your own time at it. There's no rush. Tic-tac-toe just happens to be one of the newer ones, so you'll see a few people on it right now, but it's also really hard when there's so few people on it. You can't get very high up the ladder, but if you get to silver, that's also good. Alright, so if it's open, so now we have an open state, and we're going to do a really stupid prediction here first. We're just going to do this. Let P1C. Yeah, well, hopefully you can get by the Wood League in tic-tac-toe because it's only a single little board. And our strategy, we didn't have a strategy. We just filled in from the top left across the rows going down, and that was enough to get out of Wood League. So you don't need any strategy in Wood League. Just play the game and fill in from the top left going across. Whatever empty space you have, just take it, and that's enough to get out of Wood League. Because the boss plays at random, and that pattern is enough to get by it, I think. Once you're into bronze, then you actually have to do the full game, and that's actually pretty complicated to do the full game, and then you're actually going to have at least a minimal strategy. Self.board 0.count ones. It's better be P0, P1C. Count ones. So, if P0C is greater than P1C, we do game result, win 1. Else if P1C is greater than P0C, game result, win 1, win 0. So all I'm doing is counting the number of positions that person has on the board. So if there's more X's than O's, X is predicted to win that board. We can worry about improving that later because it's actually the form of the board, but we have to make it really cheap too. We can't do something expensive. We have to do it really, really cheap. Else game result closed. Else the game is closed. It's just nobody wins. Predict state. So now we have the big state, and we're just going to count up the predict state of all the small boards. And we're going to do play 0 score. Player 0 score equals 0, mutable. And again, we could actually do this in one big sort of summing state, but actually I'm not liking the syntax of those. They get too hard to follow. So I'm going to do a traditional loop so we can clearly see the following here. And then what I'm going to do is match self.small i.predict state. Game result win X. We want to say if X equals 0, then 1, else negative 1. So anytime 0 wins, we increment a score by 1, otherwise it's negative 1. Everything else, we just do nothing. And so I say this would actually map well to, actually no, we had to do this, P0S plus equals and 0. We could actually do this in iterator sum and stuff, and maybe we should, I don't know. Because now at the end what we do is we say P0S, and this is getting redundant, we've seen this before, is greater than 0, then game result win 0, else if P0S less than 1, so he's lost the game here. So player 1 wins. And we don't actually know who player 0 is. We could be player 1 or 0. That's why I have to be careful that we always make sure 0 and 1 work. Otherwise, game result closed. Otherwise, we predict a tie closed. So now we have a predict state. Let's compile that first, or cargo check it just to see if it actually didn't make errors, because we always do. It's 142. Return Q. 314. 0S. And what did I do? What's it complaining about there? I think it just got confused from before. What? Ah, else if. Game result, type something wrong. Okay, good. Thanks, Huntress Girl. I beat the lag, though. I really wish Twitch had less of a lag. It's got an excessive lag. You guys have to be like super fast. See 1 minute into the future. Okay, so we got to predict state. And the idea here is in this strategy, play to end. Play to end returns a game result. Play to end is going to take another value here, and I'm going to put this on a new line. This is getting too long. Max steps, and this is going to be probably an I-32. Doesn't matter what it is. Let mute step equals 0. And we're going to say while step is less than max steps. If we ever get to this point, so I'm going to say step plus equals 1. If we ever get to the point where we've run out of steps, we're going to return the state, the predicted state instead. State.predictState, and just return that. And this means we don't go as deep, but it means we'll get a better breadth of evaluation. Whether that helps us or not, we don't know. That's the problem. We just don't know whether that helps or not. We're going to find out. So play to end, we're going to try with a very conservative 20, because we saw it usually goes to 40 deep. And the idea here is to increase the iterations. But because the calculation of predict state takes time, we don't know if we're actually going to gain anything from it. So, predict state. Let's go do a play. So we definitely get a lot more iterations. That's good. We get a lot more iterations. 2.5 times improvement again. Remember when we ended up yesterday, these numbers here are about 90. So we're getting tons more iterations, but this is now a prediction. This is not a valid score anymore. And these higher numbers, they don't get any higher, because we're already close to the end of the game, so it only makes a difference near the start of the game for the initial moves. So, let's cargo build this, although we technically already built it. And we're going to submit this thing. Where are we now? We're going to see if this actually gets us higher. Dead 24 at 30 score not changed. So, let's play against Amira here, Fenrir. Make sure we haven't screwed up. I don't know if we should be watching this number. If we win faster, does it include our strategies better? But if they're doing random stuff, it's really hard to say what the quickest force win is going to be. That'd actually be a curious local simulation. We should just run a simulation and see what's the minimum number of moves to win a game is. Just through randomness, what's the lowest we can see? Because we would have to have probably 6 moves. You could probably set it up and use 6 moves. Okay, but let's submit this. Let's see if we actually get any better now. I'm going to drop down to the bottom. We were at 24. Now the reason for increasing that number is also that if I can get that number high enough, and that number now is quite high, even on the low iterations, if this number is high enough, this starts to look positive for doing the predictive branching in Monte Carlo to evaluate the ones that have a higher chance of winning more, and to do the second step mini-max for the opponent. We haven't done that yet because we never had enough iterations, but now at getting this number of iterations, and again this is actually for 9 cells and this is 1 cell, so these are actually add up to about the same. This means that we can actually get to the point of, so that's our 1 turn divided by 9 for them, even by 500, we actually get to the point we might be able to start predicting what move they're going to make. And that's sort of the mini-max aspect of it, is that with this tree depth, if I actually go to a tree, which is actually going to cost us more time unfortunately, we can start predicting what move they take and focus on those branches and those other ones. And because that gives us a higher thing. Because like if you have a move, if you're 2 moves away and you look at theirs, there's no point looking at moves of theirs where they lose, because they're not going to do that move. They're going to do the move that gives them a better chance of winning. And if we focus on that one, it gets us more iterations in the winning branches to see, well, what can we do? Maybe we should avoid that move. But keeping this tree, and this is going to hurt, keeping that tree around is going to cost us a lot of iterations. So whether it's worth it or not, we don't know. The other approach is actual heuristics. When we don't have a good confidence value, do something else to pick out bad boards and stuff, but we don't know that. But that is something that could be locally trained. If you start doing heuristics based on board state somehow, I wonder if a 1-level neural net could actually train that. Given the 81 states on the board, could we train a neuron or set of neurons to tell us what a predicted state is, to get us a good score for predicted state from this prediction who wins? That would actually be really cool. But neurons have the problem, I don't know if they can play this game very well. You might have to do multi-level. 1 level might not be enough, because there's no way to draw a single line through those states and get any sort of partitioning. Well, let's see if this actually helps us at first or anything. You know, we're at 40 and it says down. That could be random. We don't know if this helps or not. We get more evaluations, but we don't play to the end of the game, so we don't know for sure. And it only applies to the initial moves, where the end moves may be more important. But the end moves, there's not a lot we can do. What else could we do? I'm really trying to avoid doing the multi-level thing just because it's hard to set up. Let's let that run. Limit play to end moves steps. I want to see if it makes a difference, because that's a number how far we play that we can actually tweak a bit. And then we can combine it back again with the actual 1-level Monte Carlo at least to decide to do the sorting here, which actually hurt us a bit. But we have to see how it works on its own to begin with. And then once we have that, we can add this value back in. We can add the sorting and preference to winning branches. And if that helps... Winter Squirrel, Apparently yes, except you only get one core, so it won't help any. That's what I was told. We haven't checked it yet, and I've done no threading on Rust. So we could run a thread, but again, you're limited to one core apparently, so I don't think it'll make a difference. I'm not sure on that. I'm guessing what there does is their game driver, in the leaderboard, every game driver gets one core. I play, then the opponent plays. I play, then the opponent plays. But I have thought of a way that maybe you could cheat. No, I mean, yes. There might be a way to cheat. If both players are running on the same core, instead of waiting for standard input, during their turn, I could keep calculating. And I wonder if that's actually possible. That would be the one curious thing to do, is that, so instead of waiting for my turn, I could keep calculating. And that has a double effect of slowing them down if the core is shared, and also giving us evaluations. Somebody commented here. Oh, attempted reconnection. So it's something I wanted to play with. It feels like it'd be cheating, but if it works, that would actually be a massive advantage. It'd be like awful interference, and it would really hurt the other player. I just wonder if it's possible. We'd have to learn a lot about asynchronous reading. So basically, we'd have to keep doing stuff, and as soon as we saw something in standard in, yeah, but I have to learn async reading first. But maybe there's a way. Maybe there's a quick way. Yeah, if I could do thrash calculations, that'd be the quickest way. But I have to get the async reading, and we could actually test that. You know, actually, that sounds like a fun thing to test. Let's see how this comes out here first. So we're going up at 40. Let's leave it. Let's see how that would actually work. Rust asynchronous read. I have no idea how this would work. I don't really need asynchronous. I just need to do a check to see, is there input waiting? Well, we don't even need threads for this. All we really need is on standard in, if we have a way to pull for data, okay, so this is going to be an issue because their standard I/O implementation, standard in, doesn't let me pull for data. Let's check if there's a way to do it. Rest pull stream for data. Must be very explicit. I want the cheap way that doesn't include a thread. I must be able to get down to the lower level interface. It's not what I want, but maybe there's something in here interesting. I'd really just like, because they're supposed to be, you don't need asynchronous read. You need, the lower order C functions have a way to say read 0 bytes and say whether there's something on there. What is standard in? Let me check that again. Standard in is no, it's nothing. There's no inheritance created by our standard in. What do we have? A readable guard. Locks this handle. That sounds good. What does it return? returns the buff read state. Well, Neumann, I don't... Do you think that would be bannable behavior? I'm just curious if it would work. If it works, I won't use it, but I want to see if it works first. And then we'll submit code that doesn't do it, because I'd just be really curious to see if it actually works. So we're up to 37 now, still going up. And it lets us learn something in Rust at least. We can read. And what does read do here? Yeah, a contest possibly, I mean. Because it would, if this actually works, it'd feel really, really cheap, right? And who knows? Unless they're evaluating all code, though, contests would be different. But, you know, who knows? Maybe the guy at the top's already doing this, right? I just want to confirm the theory. So how do I buff read this? Required methods fill buff. Okay, so we have this read until. The only problem is when we go down to this low level interface, I lose all the nice line input stuff. Oh, there's a read line. An empty buffer will indicate that the stream has reached EOF. But end of file doesn't mean end of stream. That just means the stream's ended. We can't actually check if... No. There doesn't appear to be an easy way to check this unless we do a streams. Buff read. Let's just go down to read. Winter squirrel, yeah, you know, you'd really... That would be logical, but we don't know if they do it. I'd like to confirm that. I mean, I don't want to put too much effort into it, but yeah, it'd be easy enough on a Linux backend to just pause the other guys. Just pause it entirely. Just say, screw it, you're in the background. Read. Pull some bytes from the source into the specified buffer, returning how many bytes were read. This function does not provide any guarantees about whether it blocks waiting for data. Ugh. Do we have any non-blocking calls? Rust non-blocking read. Oh, there's a question right there. This answer is wrong. Most operating systems default. That's not necessarily true. I mean, it's a flag on the thing. You just call one function. Okay, so IKFS, we're just trying to do non-blocking read, which appears we're going to have to do a thread. Because I doubt those crates are available on Coding Game. MIO. Yeah, if this isn't a standard crate, we're screwed. We can't use it then. Yeah, we can do that. I'm just trying to do a quick way, Winter Squirrel. I don't want to invest a lot of time in getting this working to get a cheap thing. But this has non-blocking TSAP, non-blocking IO, MIO. But, well, let's actually just put extern crate on the system and see if it happens to be there. Turn this off for a second. Extern crate. Let's maybe there's a chance they have the crate there. Well, it's not extern create. That'd be the first problem. Oh yeah, it can't be. I can't remember the logic. The string crate has to come later or something. I don't know where these things have to come. Hey, Cries! How's it going? Alright, so we can't use MIO. So we're out of luck there. Thanks, Cries. Yeah, that's I already screwed that up. Some has Tokyo. Let's see if it has Tokyo. Nope. Alright, so we can't use non-blocking I/O. So if we wanted to test the theory, we'd actually have to set up threads, and that's way beyond what I want to do right now, because you have to send the queuing to the front thread and work it, and that could actually cost you a lot of time, because you only have so much in a turn as well. We're stuck at the same spot, so the predictive thing bought us nothing. And an odd chance, let's check Tokyo Core. Nope. IKFS, quite possibly I could do it that way, but then I'd have to worry about how to actually get the data into a Rust string and stuff, and so there's a huge overhead just to do that. And I was just hoping if I could do this test quickly, because it is cheap, and we don't know if it works. If I can't do it quickly, I don't want to invest too much time in it, because it would be essentially cheating if it worked anyways. Okay, so that didn't work. The score prediction got us to the same place. Yeah, I don't know that far. I mean, okay, Cry. So the idea, what we wanted to do is that we wanted to see if cheating's possible. And by cheating, what I mean is that when we're waiting for our input, if we just burn the CPU and prevent the other person from calculating stuff, so cut down the time they have in half. And I was hoping for an easy way to do it. But I don't know an easy way to do it. And I don't know anything about threading in Rust, so anything involving threads is going to be hard. I was just hoping for a non-blocking I/O, which would let me do it really quickly. And we just wanted to test the theory, but apparently it's not easy. But notice something here is that limiting moves to play to end hurt us. So having a depth is not good. Or at least not. Let's go down to 30 deep and try that. That's almost the entire game though. IKFS, yeah, we're timing our moves as well. But what I'm saying is the reason why that might help, yeah, the reason why the interfering with the other player may still help is because if you are timing your moves, you're not going to time out, but you're going to find that you have a lot less calculations done if we're burning the CPU. Because right now we're also doing a timeout. I give each turn 90 milliseconds. I'll look at this channel stuff afterwards. And I'll have to figure out the channel stuff, but super easy for something that was Rust, sure. I mean, but I don't know that stuff, and I'm going to look at that maybe afterwards, how to channel the data, because it might be interesting to see how that works. Okay, let's submit this guy. So I bumped up the count to 30. Neumann, yes, a few points different, fine, except we were at rank 35 compared to 25 before. That's a major difference. And we were always settling in at 24, 25, so whatever we did, that was enough to show a difference. And I'm submitting again with a bigger depth to see if that actually helps or what the difference is. Mr. Pepperoni, I'm in Germany, but I'm not from Germany. I'm actually Canadian. I've been in Germany a while now, though. That's why the show is called Evening Rust, not Midday or Morning Rust. Because for me, it is evening. So with the scoring I did, this is the depth. I go to a depth of 30, and to 20 it didn't help any, but we may have to combine it with it. Maybe our heuristics wrong. Again, the predict state may actually be wrong. Very hard to tell whether predict state is correct or not. But I have to find something to tune. So far we don't have anything to tune. But there's obviously people who have a better strategy. Unless you're just getting deeper. That's the only concern, is we can't really tell unless they're just evaluating more moves. So we're going to check the languages that are above us in the charts once we get back to 25. Let's just look at the top languages. And now there is a Java one here, but with a JIT compiler, the type of evaluation is doing, and if you hand-coded the optimization in Java, you can still do quite fast. Obviously, all these C and C++ ones are disconcerting. These guys may just all be calculating more. And I mean, they're still in debug mode, but they still have, well, they have the option of forcing it into release mode. Go, I don't know how fast of a language that is, so I can't say. And we're above the C#, so we should be in the 25 range. Okay, but this one here, JavaScript at 33 is a good indication that there is a way, some heuristics or some calculation that we can actually improve the score, because there's no way this JavaScript one is solving like thousands of iterations. Cries, we have one. This is why we don't parallelize anything. We got one core. And we don't have any external crates. I'm willing to bet this is actually like a... And this is where the difference... I'm willing to bet this is actually on some hosting server where you actually get one virtual core, so you probably don't even get advantages of hyperthreads. And to be honest, what we're doing, hyperthreading doesn't help. Hyperthreading is that trick where you have memory access, and we don't have that. We have pure calculations, and pure calculations is the case where hyperthreading actually slows you down. you would actually have to have some sort of I/O to get advantage from hyper-threading, and we don't. Our code just doesn't have that. Rust threading stuff. Yes, I know. Threading is supposed to be very good, and we're going to have to get into that. And it's the one limitation in coding game that you don't get. Well, we could do multiple threads. We could just do it just for the hell of it, but that will slow us down. And I won't do it today, though. What other strategy can we have? We have the first play heuristic, but I don't think the first play makes a big enough difference that we have to care. Or does it? Who thinks that the first move played on the board, when I play first, the first move makes a big difference to the game? We could calculate this, but yeah, well. Let's actually calculate it. While this is running, let's actually calculate it. Yeah, I doubt it as well, Kraz. I just can't imagine it making a big difference. Well, that was my theory, is that maybe there is actually a best first move. Instead of just assuming it's center, let's calculate it. Let's go over to play and let's calculate it. No, I don't want to be lazy. I want to calculate whether I should solve. Fine, we'll just do the top player. And then we'll confirm it afterwards. Well, he's going to do second move. Does it vary randomly who goes first? IKFS, there just isn't. Not in Rust. So I went first. How do I get him to go first? Do I just change the order of these guys? He definitely seems to want to get the center square, and based on my 2 runs, and this is what I'm part to say, part of the scoring, we can improve the scoring to say anything that wins us the middle gets a better score. Yeah, so maybe we should improve a heuristic. And he's definitely targeting the center. IKFS, there is another way to cheat. There is, apparently you could bundle it up to a binary blob in a C++ or something and submit it that way, but yeah. And ASM is probably the approach you could do that. Well, then we're going to hand code that. Why is it? Oh, it's starting to get hard. Okay, so they prefer the center square. And do I want to do in the first turn? We just want to hard code one bit of logic, and I had to figure out who I am in the first turn. Let's get rid of all these print line stuff. Discard the rest. Actually, do it this way. Four comma four. That's dead center. I don't think we have too many checks though anymore, Cries, and we've gone through the code for optimization and the bits because we're in debug. Remember, we're in debug mode. That's a big part of the issue. But even if we're in release mode, if everybody was in release mode, we'd have the same issue. So we don't know. Okay, 4-4 is dead center. This is linear indexing from the top left. Yeah, release mode would definitely be better because we get Rust is a bit slower in debug mode, I think, than some of the other ones. Now, where was I on this one? Where do I get up to? I want to compare first. I made the depth deeper. We're still going up, and see the turnaround time makes it hard to test some of the stuff as well. Cargo build. I'm going to keep playing against Recurse. If we ever get a win against him, it means we're close to the level, but I don't think we ever will. No, I wanted to change it so I go first now. And I should play dead center when I go first now. That's the change I just made. So far it's been variable winter squirrel. I can check roughly in my head, but yeah, benchmarks would, wouldn't make sense. We've done those before. But the logic also changes, so that's why it's a bit hard. We expect the performance to change because the logic changes, and we do different things. So it looks like we might have just been pushed down the chart right now. And aha! That's an interesting approach. Moderated seal. I lost! I lost again. Well, this is weird. Doing my first move dead center is causing me to lose. There I won once. Against myself. What we can do is change our heuristic then. So we have an actual history. Take first move, and we have one place. No, it's always the center, I think. But this is super tic-tac-toe, so it's hard to say. And yeah, in normal tic-tac-toe, if you play the center first, unless you screw up, you can't possibly lose. So, predict state. We can adjust this now. Predict state. We can start adjusting this by doing this. What are the next most valuable positions on the board? Probably none. Probably just the center. So we can do this times if I equals 4 curious now. Wow, it's a corner. That's almost counterintuitive. Well, we can start playing with this though. How much more should the center tile be worth? Let's say 3, else 1. And we have 2 places that predict state. And well, let's just stick with that first of all and see if that makes a difference. So all I've done is the predict states. Yeah, I'm missing something. No, I'm not missing something. I equals 4 is correct. Oh, right there, that's correct. Sorry, that's the typo. Yeah, thanks. Can't see in that. But actually, let's put this move down to 20 again, because this only makes a difference if I don't evaluate so deeply. Okay, where are we looking at? I'm lost now. Where do we end up? So on its own, our depth searching limiting actually doesn't help us a lot. But maybe with this heuristic, maybe then it'll work. So we're assuming this should work. If we should be able to beat ourselves. If our code is better, we should definitely be able to beat ourselves now. All the time, consistently. If not, then we have a... No. First one we lose. But we definitely value the center more. So 52. Let's play ourselves a few times to see how that works. And we valued the center here, and it doesn't seem to make a good difference against us. So playing against myself, and I don't search as far, but maybe that's just it. Maybe it's because I don't search as far and I have that combined. Let's just try it. Let's just submit this one. And wait on this and see if it makes, because I reduced the search depth enough. Because again, the key is if we can get the iteration count high enough, If we get the iteration count high enough, then we can actually get the second part of the Monte Carlo to make sense. Yeah, Cries, that would actually make sense. And but millions of games is going to be hard, right? This because it's time based. So what I mean by that is that our game locally, when they take 50 moves, that takes 5 seconds to run one. So we can't run millions. Every 5 seconds we can run one game. I mean, I have 8 cores, and so we don't gain a lot by running locally. It should be a little bit faster, but it's not a huge gain. And the only thing I can see running locally is that if we had something that's trainable, if we had a trainable heuristic in here somewhere, we could actually train that locally. Because we could let the Monte Carlo run millions of games for a move and then say, well, which one's better of that? But we can run a... Actually, wait, no, Cries. We could do it, because if we limit the iteration count to what we normally get, if we say we only have 10 milliseconds and run release mode, that might be equivalent to running in debug mode with 100 milliseconds. So we could actually do it faster locally by doing it in release mode. But we have to be careful that it's not just the depth that's winning, because right now if we just run a release mode, it's the depth that's going to win. Now we could improve the heuristic on predict state. There's something else we could do as well. We're just counting the X's and O's right now. But there are a lot of boards where if you have... Let's get out of here for a second. I'm trying to see if there is one here. There's a lot of boards where, like, say this one here, if there was another O right here, I couldn't prevent... I can't... No, if say there's another O... What do I mean? Where's... If you have 2 winning conditions, if the person on the board has 2 winning conditions, that has to be evaluated in their favor. They automatically win that board. You can't win that anymore because they're guaranteed to win it if there's 2 winning conditions. Except, no, shit. In Super Tic-Tac-Toe, that's not correct, because in Super Tic-Tac-Toe, it doesn't alternate turns, so there's no guarantee of that either. So how else could we improve the heuristic then? Where are we doing? Well, we're doing okay with this, but we tend to bounce out at 45 anyway, so I let this one run longer and see if we get any higher with that. Now, let's let it play in the server. Let's do the actual Monte Carlo thing now, or the Monte Carlo tree bit, and play against ourselves on the server. Let's see if this lets us win every time against ourselves. Watch the first one to lose again. Alright, so 1 down. This could be automated locally at least. 2 down, that's a bad sign. And we consistently lose, and that's scary. So the attempt to actually do the tree heuristic to improve looking down the bad path is actually just screwing us up. Wow, that makes it worse. And I know why it makes it worse. I'm evaluating the losing paths because I'm sorting by key in order. How do I do a reverse sort? Shit, that's Rust. Reverse sort. Well, I guess sort by key. Screw it. Reverse sort. Just do a minus of this. That could make a big difference. Well, we'll find out right away. Now let's play against it. Now we should win all the time. So yeah, I was optimizing the bad paths there. Still lose. Come on. Come on. Don't do that to me. Prove to me that my logic's supposed to help. Did I build this? Did it not submit or something? Well, that's bad. It buys us absolutely nothing. It makes it worse. And this is my fear with the low iteration count. With a low iteration count, you can't do branch optimization. Because it cuts off the other branches so much that you could actually end up missing a good path. Okay, but that other approach seems to be doing all right. So what I mean by branch optimization is that in the Monte-Carlo tree, our one-level tree, as we start evaluating our potential moves, we have them broken up to 9 at max, probably around 5. As we start evaluating moves, some of them start to occur as pure winners. They have a higher score. So they have a higher score, and we're looking, okay, we want to improve our confidence interval. So the ones with higher score, we sort by them, and we evaluate them more often. This is the RPT here. We evaluate them twice as often. Any ones in the high list, we say, well, let's evaluate this twice as often. And so we get more results for it. And when we sort again, it'll shift them out. And so the idea here is that you're gonna double check. Is my winning one a really winning one? Should I go there? But at the number of iterations we do, and okay, I don't think this sort's causing us any grief anyways, but yeah. But okay, the key is that no, unstable's totally fine here. We don't need a stable sort. Unstable would actually be better. If it would randomly switch them, it'd be perfect. But as I don't think we have enough iterations to take advantage of this. We're just not playing enough games to go through this well enough. And where are we now? But we could try something else, though. This death-based searching's killing us. Let's do it with a very low search depth. Let's just go down to 10. 10 moves is like virtually nothing. But that gives us a hell of a lot more iterations. There's no unstable sort by key. That might be something new. I think middle of last year is the version they installed. So middle of last year. Now this is really sad. Absolutely any attempt to optimize path selection just causes us worse. Just makes it worse. Okay, so maybe it's just not there right now. But no, my compiler's fairly new. Right, I have 1.24. And it didn't find it on my machine. Oh, okay. Sort unstable by key. Yeah, but I just removed it anyways. Oh, I meant to remove it. I didn't actually remove it because it's not helping us. Because that's not helping us, it makes it extremely unlikely that the tree of depth 2 would help us, because we just don't have enough iterations. Where are those high iteration counts coming from? I'm only doing 10 now and not sorting. We're not going to make it much higher here, I bet. It's a bit of randomness, as was mentioned, but that means everything we're doing, let's limit the depth to 40. That's like pretty much, it's just limit the depth to 90. 90 is more moves than are on the board, so that's basically an unlimited depth. And see, that's the only thing we've really changed to get back to there. And we do better that way, but let's run it again. Yeah, we do better when we don't limit the game depth. And what that means, it means our heuristic sucks. And we could, in theory, find a way to train the heuristic locally. I'm just wondering how. I'm wondering whether a neural net is actually a good fit for this. Could it actually predict the winner from the current state? But the predicting depends on what strategy they're playing, so that also makes it hard. I don't know. I really don't know about that. Let's just submit my old one again that does an unlimited depth. And what else could I do then? I'm just thinking of what other strategy I could do other than... So the actual Monte Carlo tree search, we're not doing because we don't have enough iterations to get any value out of it. We just simply don't have enough. Any attempt to do the path optimization just makes us worse. And that's the category. Every single time I do that, it's just worse. Our heuristic is the one thing we can improve, but that's the one thing by hand, I don't know if I can improve that. Could we actually improve that? It's hard to know. Like, if I just look at the boards, I can't decide what's actually a better board position or not. So that'd be something we'd want to train. Because if you could train this, if you could come up with the equation for training it based on 81 inputs, and the game has 81 inputs, could we create a little neural network that predicts the value of the board? But in order to play that, we'd have to train it millions of times. I could let my computer run for days. But we'd have to prove that it worked first. Because the neural network values then are going to be tiny, and you could just plug them into the code. They'd be hard-coded, but the training is what takes all the time. And that would be the next step, I'd say, for what would make the most sense. But again, here, what I showed is that the heuristic sucks. And this, right now, we're not using the heuristic. I'm just doing evaluation at the end. I don't do play limiting. The only way we'd have to do is prove that if we limited the depth of search and we got a heuristic that works, that would be the next step. Or we find hand-coded strategies that somehow work. And that's really the only option I see. Either we improve the number of iterations, which we can't. We're not going to get more. We've optimized that as much as we can in debug mode. Because we don't have enough iterations, we can't really keep a Monte-Carlo tree because the branches will have like 2 items on them, or 3 or 10, which is totally useless. Which leaves the only possibility is to reduce the branch search depth and do heuristics. So heuristics are the only option we have. Now there is one heuristic, DBS. Well, I studied programming, computer science a long time ago. Most of the machine learning AI stuff I've just done from various things. I don't really not very good at it. This is the most I've ever done with AI as coding game here. I've not done much AI before this. So I know one way we can improve a heuristic a lot, and again, the heuristic only helps if we trim the games. You notice the games only go down to 58 moves, like 40 to 50 moves, so you really have to trim the output to get a better idea of where it goes. And there, I like to see this, just, you know, hey Euler, we beat you twice. Sorry. DBS, yeah, I really follow the theory quite a bit. I like writing articles about stuff, and especially complexity theory I know a lot, and I'm really learning it now, and I really try to make sure I know this stuff, because if I get to sit here talking about it, I at least have to know something so I don't sound like an idiot. Sorry if I do sound like an idiot, but if you're doing algorithms programming, this is clearly algorithms programming, you have to understand where the things are to improve. Alright, so this is the base. This is basically where we started the evening. The one that's running now is the one that started this evening off. So let's put ourselves back in there in the arena code. Does anybody know if I add my arena code, is it always the current arena code or at the time I added him? And we're going to go back and we're going to do a force to depth, and the depth has to be really cut off to make the sense. We're going to do a depth of 20. Each person takes 10 turns. And in the heuristic, we're going to change the predict state. We're going to create a new board. Let B equal... What do we even call these things? Small board. Small board. Default, or is it default or new, or what do I call it? Small board has a default. Good. And I can do a set player lin on it. Set player lin. That's what I want. What I'm going to do now for predict state, instead of adding up the small boards, I'm actually going to plot the predicted state to the small boards on a big board and then return the state of that. That seems like a much clearer heuristic, because otherwise the counting is not fair, because if there's an actual win, it actually wins. So screw the score. That was a dumb idea. No, it was actually reasonable. Win. If there's a win, then we set something on the small board. Okay, thanks Euler for clarifying. When X, we do set player lin at I, comma, X. That player won. And it doesn't matter if they win or lost. Well, it does matter if it's a tie. Oh man. Predicting states is hard. I wanted to do both, actually. If there's a win, we also do b.set player lin I, x. And then we have this. And then we're going to do this. We're going to do match b.getState. It's actual get state now on the small board. Game result win. Can I just do this? I'll just return a game result win x. I don't know if I can do a pass through. And otherwise, we're going to predict it based on the score. Right, so what I'm working on here is to predict state. Before I was just counting up the mini board scores, and that's actually not very clear because if one of them wins, it wins. So instead now, when I predict the state in each of the small boards, I plot it on a new small board and also keep track of the score. And I'm going to get rid of this bit for a bit. And then I check if somebody wins the small board, then they've won the game. Otherwise, we go to the scoring bit as well, because the game is still open. All right, and where are we at now? So yeah, our best strategy is the one we started the evening with. Just search to the end. Don't do any heuristics. Don't do any sorting. And we're trying to beat that. So we can just keep playing against ourselves, because until we can beat ourselves, it means we're not doing any good. This predict state now becomes expensive, and that's the problem. It gets more and more expensive the more we do with it, which limits our number of iterations. Let's play ourselves. This should win every single time, otherwise it's of no use to us. So yellow has to win every single time, or at least tie. No, it should win. So 1-1. And it didn't win a definitive victory. It won by like closing it off after 55 moves. Okay, so it won this one. I think it tied the first one actually. Has anybody proven if this game is forced? That is... Can you force a tie or a win in this game? Does anybody actually know that? This is interesting. Every single one we've played so far, we've won. That looks promising. What? It's going to be second place now. Ah, broke my streak. But actually it was doing well. So let's run it a few more times and then check. Because I was doing well. And there's tweaking values. The reason I like the heuristic approach is because we have values to tweak. No, we lost again. We lost against ourselves. Because the Monte-Carlo approach, there's nothing to tweak. You don't have little things that say, we'll do this instead. We just have nothing there. In the heuristics approach, we have values because right now we could change to predict state, but in this strategy, I put us down to 20 moves in the future. That's not very far forward looking. That doesn't give us a very good impression, but it's something we can modify. And ideally, we like to test that locally, but it's really hard to set up multiple versions of ourselves locally unless we had configurable strategies. Okay, we're going to see where we go today, and we're going to see when the next league opens up, whenever that goes, because if I do continue on tic-tac-toe, I'm not positive of this, and we're going to another one, then we will restructure to run it locally, because that would make sense. And that means we have to be able to configure a strategy and compare it locally, and we just keep paying who wins. But everything has to be configurable then, which makes it harder. Alright, so let's just submit that. We were at 26-25, where we were on the show started. Our goal is just to get past that. If we got to 20, it would mean there's improvements. Who all is actually still submitting? So nobody of these guys are submitting. DVR is still improving his code. But none of these other guys have submitted in a while. So they check code, but okay, Maxime is submitted. So there are a few submitting, but mostly not. Just our lonely ass self. And these a few other guys. We can't possibly, but that's our old code still. And show the new code. Well, that's an initial nice jump. I mean, it seems unlikely. Really? Guys, that would be delightful. On the function declaration? Which functions do I want to inline? Unfortunately, I want to inline the Rust functions. Let's check this out. That would be wonderful if that actually did something for us. One function in particular, get global RNG. I don't know if that bought us anything, but which other function do we use a lot that costly? And this thing here. This is a tiny function. It's not costing us speed. The variation is so much. This is a problem with random. The variation is so much that... Where's the X get state? Are you sure this inline's even on debug, though? It's not buying us any speed improvement. Take turn. Okay, set player lin. We know this one's called, so let's do that. Get closed mask is something we'd want to inline. Just trying to see if any of these increase. That one had a moderate increase in the average, it looked like. It's not creating enough of a difference that I think it's going to make a difference, but maybe a few. Maybe it's different on the server, maybe it's just my visuals are not good enough. If we get to 25, that would be nice. That would prove the heuristic approach could actually work. What else can I inline? Let's just go inline crazy. Get board cells, not called very often, but that seems like something that should be inlined. Print row, print we don't care about. Get state, we inline. Predict state. And Tomcast, yeah, I know. We actually did that in one of them. We set up benchmarks. Can I set them up next time, though? And we can turn them on and off. I have outputs. I mean, visually I'm seeing outputs, so it's not like I'm guessing this at random. These iteration counts, the problem is we have too much randomness, and I can't say for sure. Right, I can see from these initial counts, and I'm basing it based on this, whether it's helping. And these numbers are slowly going up. Just not a lot. And this predict state could also go inline. I don't know if this is used anywhere. This is probably not used anywhere, but let's just do it on all of them. Set plays is actually not used anywhere. Next free. But Tom, that's because of the randomness. We should actually use a fixed seed for local. If we use the fixed seed in the random generator, it'd be better if we did it. And that's what I mean, we'd have to do a lot. We know this one was costly. And so Tom, I know there's variance but if there's not enough of a difference, I could definitely see it. But see, like these numbers here, these are enough numbers not to see variance. Thanks, Christ. So this should help, and it's wondering why it doesn't help. Probably because it's not the inlining. It's probably not our function overhead that's causing the problem. It's the actual Rust stuff. So I mean, based on the variance of these numbers and stuff here, the numbers aren't changing enough to say that inline always is helping. Like, if inline always was going to be this great boon, these numbers would have jumped up significantly. It's not like it's maybe we got 5%, maybe we got nothing. The inline stuff is definitely not getting us to a point where it's like saying, hey, this is awesome, but it's also not costing us anything. And so some of the numbers are definitely higher. There's a few runs where it's higher, and it's really hard to say with the randomness. I could turn it off. But let's try this in release mode as well to see how far this really gets in release mode. But release mode is going to be probably inlining this stuff anyways. Like, if you notice in release mode, this is just like, the difference is unbelievable, right? We go from like 600-700 iterations to 10,000. So we get around 13 times as many iterations. And these ones down here, these are just awesome. Like, look at some of these iteration numbers here, like 87,000 iterations. This is the realm where you could actually do the Monte-Carlo tree stuff better, because at this number of iterations, you could actually preserve stuff to the next round and actually do the sorting, and that would actually get you better. Twitch loves to lag. They never want you cheering for somebody when something good happens. It's always... Where'd we get up to? 32. Come on. Still going up. I like this. This actually confirms that maybe... Yeah. And yeah, Tom also said the issue with benchmarks too is that when you're running in debug mode, there's a huge variance just in the way it runs because of the way it compiles. Because you use more memory and stuff, and so the eyeballing is actually probably as good as we're going to get with benchmarking. And from all that stuff we're doing, so we're fundamentally have to look at algorithmic improvements. And that's what we've been doing here is algorithmic improvements. The inline always is not an algorithmic improvement. For example, this play to end here, if I put this back to 90, we'll see those counts drop, the initial counts. Right? And you see that they drop very clearly down to 300. You get very few iterations. If I put this up to 10, we're going to get a lot more iterations. And this is where the heuristics are very important. So now we jump up to 1,000, we get 300 more, but we're relying on a heuristic a lot more. Is this thing good? Is this move good or not? And so I say that's good if we're getting up here in rank, it's perfect because it means that we can actually play around with that and see what happens. But we're stuck at 34 again, which means the heuristic stuff is doing worse than just taking fewer iterations and evaluating the tree. And I think this was the issue originally with Go as well, is that if you look at a board, can you predict the value of the board? And the heuristic approach comes right down to that. If you look at a board, like right in the middle here, can you predict the value of this position? Can you say from this position who's more likely to win? If you can, then the heuristic approach is awesome. If you can't, then the heuristic approach is totally broken. But because of how we're doing the leaderboard with a low heuristic, and it's still going up, so it looks positive for the heuristic somehow. Like there is definitely value there. And if this is actually working, this is where we could take this to the ultimate extreme in doing this, is that we could try to figure out what neural network would apply here. We wouldn't need many neurons. We have 81 inputs. We have 81 states. For all the 81 states, you have either a 1 or a -1 or 0. It's empty, free, or belongs to either player, and that's the input. And what you want to train it for is player 0 winning. You want to train it so the ultimate output of the game is player 0 winning. And so what we could actually do is for every state, we predict who wins. And now this is the hard part. Then what do we train against? Then we Monte-Carlo like a million iterations of that state. From that state, Monte-Carlo, here's a million iterations. And we'll use that. Whoever has the higher score there is the guy who actually wins. So actually, no, the neural net is not going to predict who wins. The neural network is going to predict the Monte-Carlo result. That might be possible. So given the state of any board, what is the Monte-Carlo result of winning that board? But again, we have this huge variation, and wow, that's definitely not my strong point. Cries, I was thinking about that too. And the issue is that I don't know if it would help. It's because of the rules of the game. The small boards are not independent games, because remember down here, if I play an X here, that definitely wins me the board, but it then lets him play up here. He forces him to play here, so every move I do around here forces his next move. And so I don't know if a small board lookup in any way would help. It's something we could do. But we don't have to do a lookup. It's something we could do, is that we could in theory say, look, anytime we play in a small board, what's the best option to win that small board? But that would completely ignore the fact that we might give him some other board elsewhere. Plus, our heuristic would actually already include that, because in our heuristic, when we evaluate a board, it's going to say if we've won the board, we get a point for that cell, and it gives us a better chance. So, really hard to say. We might just have to try it, and we're stuck at 30. What I want to do is an experiment here. This depth of 10. Let's only go 10 moves into the future, and do board prediction on that. And see if that gets us anywhere. Go for it. Alright, I am almost done for the evening though. We'll go to about 9. Obviously this is not 29, unless we got lucky. That'd be really weird. Okay, that makes more sense. 69. So it's really easy to get to the top, and I mean, this is just the nature of the competition because we don't have leagues, is that we're probably not in the Silver League anymore. We'd probably be up in the Gold League with the next people, and so this league is split into two halves. This league is basically the people that are in Silver League and their bot's not quite gold, and the people at the top that are probably Gold League. And because it's not split yet, we're going to rocket through the bottom stuff no problem, because we're definitely past that. But at the top, we're just sort of hitting at the point where are the gold people. We don't know where that cutoff is or how well we're doing. And Kreis, yes. And based on the way we've set up the heuristic now, that's essentially what we're going to be doing. Because if we look at the heuristic, what I'm doing is, on the heuristic predict state, this is why I say the small board here is I'm taking the wins of the small board, and this is setting up the big board. And if the big board has a winning state, it says it's 1. And so this heuristic here prefers us winning the big board. It very clearly says whatever lets you win the big board is very good. And the small board prediction then is... Yeah, I know what you're saying. And we're essentially doing that, but we're doing it in a Monte-Carlo fashion. And the question here is, could you ignore the depth of the game and focus just on the high level? And that's a definite option. I wonder how hard it would be to write the strategy. So the option here is that, as Kreis says, is that adopt that and say, well, screw it. Let's ignore the fact we're playing super tic-tac-toe. One strategy is that on our turn, if we get to pick anything on the big board, we do a Monte-Carlo on the big board. Haha, there's only 9 moves. We can do a complete evaluation and determine who wins. Good, we could do that every time. And then pick which square we have to go to win there. Now on each little square, we do the exact same thing. We assume every little square we want to win. And we pick the best move for winning there all the time. The danger there, of course, and the reason why it might not work, but we could test it, is that when you play in the small board, it gives the it forces where the next player goes, and you may have inadvertently played into their hands. And so the full Monte Carlo approach avoids that. The full Monte Carlo has a complete board. It considers the complete board where you are, where you're going to. And how hard would that be set up? That might not be too hard to set up. We can try that next time as a comparison. I don't have my strategy set up in the strategy objects, and maybe next time well, yeah, correct. And you're basically getting down to my strategy, and that's my predict. Well, what's my likelihood of winning? That's what predict is doing. What's my likelihood of winning each of the small squares, and then predict the result in the big square. And so that's... And I'm just doing it unfortunately I'm doing it hundreds of times. If I was doing it thousands of times, I'm pretty sure we'd have a better score. Now where are we? Alright, so this is interesting. I'm going to let this one run and see how high we get. We're not as high as we used to be at this point. Because what this submission right now is this submission is based on this heuristic entirely. I mean, not entirely, but in the strategy, we're doing 10 moves depth. No more than 10 down. And that gives a massive number of iterations to look through. And if the board prediction is good, that's good. But the value of a massive number of iterations is that at some point we hit the critical mass where in theory, sorting and going through the valuable options makes sense. At some point, if we have enough iterations, doing the two-step tree to predict what the opponent's doing will be valuable. But I don't think we're at that number of operations yet. We need thousands for each cell. And we've got a few hundred more. So, not a lot. It's probably, though, as we cut this depth down, the overhead of this loop becomes more of an issue. Like this sub-nanoseconds call, I don't know how long that takes. That's probably costing us a lot. Actually, let's do that. Let timer I equals 0 mut. Well, Cries, you still have to predict what space you want. So you still need some strategies to say, well, which cell do I want? So you'd have to have some iterations, and well, you can't really have a lookup table because remember, even on the lookup table, you have factorial 9, something like this. You have like 300, you have hundreds of thousands of different formats to the table. You could probably prune this down based on rotation and stuff. But there's a lot of different formats. Oh, not that many. That's too many. So you have 9 cells, 3 to the power of 9 actually. Okay, so that might work. For each state, you have 20,000 states you have to calculate. If you had a lookup table, that'd be great. But you'd have to calculate that at least once, and this is an option. A 20,000 lookup table is something we could actually do. Is given the state of a small board, what's our best position to win that board? And obviously, due to rotational nature, you could reduce this some more, but at 20,000, why bother? 20 kilobytes. Although, anybody know what the size limit is for submitted code? Is there a size limit for how much code I can submit? That would be interesting. If timer I mod. So we're going to take a chance here and say every 5 loops and see if this is actually faster. I'm just eyeballing it again. Bunch of 12,900s. Okay, so 100K, yeah, if you pack that table, you could actually get the small table in there. Alright, so this elapsed time is not costing us enough to make sense to filter it out. Oops. Where do we end up with this? Okay, so we need more depth to get up there, that looks like, because we should have been up to like 30 already. Again, there's some randomness here, but it looks like we're not going to make it as far with this one. So let's go back here and set this depth down to 30, and that'll be my final submission for today. And I'll just let that run and see where that gets us to. And I'll have to think of other strategies next time. Is that maybe we just add the benchmarks. Maybe we just finish this code off, make it some nice Rust code. We set up the benchmarks in anticipation that eventually there will be release mode on the servers. And we're going to want to actually benchmark it. And then we'll set up the local playing so we can play ourselves locally. and then we can adopt the strategy at least locally because we know we're close to the top, so anything that beats ourselves is better. And we may want to take the Cryas approach that, do we actually have to iterate through the boards? Or I'm still going to iterate, but if we ignore the full logic, if we take small boards and test that strategy and see if we just take the greedy approach, let's win the big board, let's win the small board. Will that work? It might. It might. We know it can't compete against the full Monte Carlo search, but because we're limited by the iterations, heuristics could actually work. That's always the problem, is that an iterative approach requires thousands upon thousands of iterations, which we don't actually get there. We do quite well with it, but not well enough. Whereas a heuristic approach can include more logic. It can't find new strategies, though, and that's the limitation. And I talked about that when I did the post-mortem for the botters, is that when you have heuristic approach, that's the biggest failure, is you don't find new strategies. It's whatever you've coded into the system, whatever you've hand-coded. But the dual approach might make sense. And that's why I say, if our heuristic thing here is working well, could we actually train a heuristic? Could we train a heuristic to predict what the win rate is of a board? Given any board, do we have a way to actually train it to say, well, this is the actual outcome? We can do it based on random plays and use Monte Carlo, but I don't know how to set up that neural network. Because I highly doubt a single neuron with 81 inputs is going to work. It's going to need something more than that. And I don't know if it can detect the patterns that actually win. I don't know how that works. It's always linear. And neural networks have some limitations. I don't know if we have to do multiple layers or what happens there. It's not my strong point. I've only done like 3 or 4 neurons at a time, and I've never done layering. No, I did one layer once, just as a test. Actually, we could do that. Knowing what wins, we could actually hard code our neural network with the logic of the game built in. So instead of it trying to figure out the logic, we could actually combine our inputs. So we can give it its all 81 inputs. Give it the 81 inputs. But then also, for each of the individual boards, give it the inputs of each of the winning lines. So each one has 8 winning combinations, and we actually have a neuron that checks that. Does it win? And I mean, you could train it long enough to figure that out, but we could just hard code it instead, right? We could hard code it and say, these are the winning combinations. That would speed it up a bit. And then for the big board, do that as well. And then we'd have a way to train it. Again, the purpose of training the heuristic is that we want to cut down the number of iterations. And if the heuristic is good enough, but we run the danger that the heuristic might come out with total crap. We don't know. We're going to have to try it. It might come out with basically saying, if you run the training comes out and basically there's no stable state. It just comes out and says, I just can't predict it. That is a possibility. I don't know for this game. I don't know whether you can predict it or not based on the current board type. There are some boards we definitely can, but we might be able to just hard code those ones as well, right? So like we could actually go through our heuristics now and we could start hard coding certain boards that are bad. Ones where the opponent has a good chance of winning, and we don't need the neural network for that. We can do, as Cry says, we just make a big lookup table for that. Given any mini board, what's the chance of us losing? But we really want to do the big board. So I'll have to see. But next time then, and this will probably be around Thursday again. Thursday I was probably going to come back. Tomorrow I might do fuse programming. I'm not sure yet. But Thursday I'll come back to this. And if I come back, we'll do the benchmarks first. Then we'll clean up the strategy to play ourselves locally. Because again, the purpose of the show is not necessarily just to win on coding game. It's actually to learn stuff about Rust and figure out structuring and go through this code. So we don't necessarily have to just like figure out how to get to the best of the thing here. And then we can find, if I separate out the strategy, I can try Kai as a strategy, we can go through it. And tic-tac-toe is a nice one because it's not a very complex thing. And there's lots of ways to play with this. And so we have many options there. And we'll learn eventually more to do with it. And yeah, I think that's it for me today. I don't know if we'll keep watching this go. It'll take a while before it gets up there. I assume I assume we're going to get back to wherever we were before, about 25. I put the depth back to 40. I left the heuristic in. We don't play to the end. This was just the final test to see, does our heuristic actually perform equivocally with the depth? And if this doesn't get up to 25, it really means either a heuristic is total crap, or a heuristic can't accurately predict who's going to win. And we're only going to find that out if we actually do the refactoring we said and do the benchmarking. Well, we don't have to do benchmarking, but it's just helpful. The refactoring will help us answer that question. Can we actually train a heuristic to detect what the board is? Okay, and so I do have one other way to speed it up, though. One last thing I haven't done. We didn't do it today. The random number generator is slow. We could actually hand code in our number generator, and the random number generator doesn't have to be good. And so we could actually hand code one of those really old classic ones that's like really cheap and just does one multiplication and addition, and that would get us like more iterations. I don't know how many, but it would definitely get us more. And more iterations obviously helps. It's been very clear, more iterations definitely helps. I have another way to increase the time. I play in the safe side by putting 90 milliseconds instead of 100. There's a 10% bonus here if I put 100, but that runs the risk of having not enough time to give an answer. So it's not going to be a good enough answer. But if you had really close to another strategy, that might help. Alright, so I thank you very much for watching. I think I'm done for the day. I'm just going to let that run wherever it goes to do the final test. And tomorrow I might do fuse coding. I'm not actually sure this week. And Wednesday I won't do anything, but definitely on Thursday I'll be back. If you want to see a Leaf stream based on what I have so far with the graphics I showed at the beginning of the show, just let me know. These were these graphics. And show you how it's done. This is my compiler for Leaf, and this is, it's not that impressive obviously, but this is completely my compiler. This is linking to SDL, and I will start doing it. I'm just trying to find when the starting is. Do you guys want to see stuff at this stage of the compiler where there's really no standard library? Do you want to wait until I can actually show stuff like how the Tron algorithm works by using Leaf and stuff like that? Because when I do it my own, I can visualize a bit better, and I'll just make them complementary, the shows. But if you want to see the low-level compiler stuff, just send me a tweet, send me a message saying, hey, I'm interested in low-level compiler stuff, how are you doing the compiler? Then I'll start streaming that. Because right now I just do it offline. It's rather difficult to actually talk about it at the same time. It really slows me down, but if you guys want to see it, I'm glad to show it. And, for example, showing the code which does this, show the defects I had in producing this, why it was crashing originally. But otherwise, I thank you very much for the time. Don't forget to subscribe. I thank for the subscription today. Thank you very much. And follow me and retweet and do all that fun stuff to increase our viewer numbers and just make the show more fun. Thank you very much.